12s. Probability trees. Actually, I don't like that word diagrams in there. Probability trees, that's what we're doing today. It is the last of the new work for this topic. They look a fair bit like tree diagrams, which we've seen before, which we use for modelling equally likely outcomes. We can determine the size of the sample space using a single stage or a multi-stage event, right? Remember that, we get those trees and the branches and whatever else. Right, follow that along. Now, we're going to use these probability trees for multi-stage events, but we're going to use them in a way where we have outcomes that are not equally likely. That's a little bit different to what we've done before. Not equally likely. Let's jump straight through to this example here. 12. I've got a fruit bowl with 12 pieces of fruit in there. Right, there are 12 different pieces of fruit. Now, if I take 2 pieces of fruit out there, I've got 12 times 11 is 132, I think. Yeah, 132 different branches at the end, and that's a mess of a diagram. Right, the way that we're going to model this is instead of looking at 12 pieces of fruit, I'm going to say that there are 3 options: an orange, a mandarin, or an apple. Okay, so what did I say? 3 options. We need to draw this as big as possible. Tell you, this is not the first time I've made this video because I got a bit messy. Orange, mandarin, and an apple. Okay. Along each branch, I need to say what the probability of following that branch is. Well, probability of an orange, there are 4 out of 12. You may simplify that, but for the time being, I'm okay with 4 out of 12, and 5 out of 12 here, and this one here, 3 out of 12. Okay, just makes it easier to see. They all add up to 12, 12 out of 12. Now, second piece of fruit. 3 options again for each of them, yeah? Okay, so you can see that I end up with 9 branches here at the end, but that's a lot better than 132. So I'm just going to go with O for orange, M for mandarin, and A for apple. O for orange. Orange, you glad I've abbreviated like that? No. M and A. O, M, and A. I know what you're thinking, OMG, but no, OMA. Orange, mandarin, and apple. Now, this is where it becomes a little bit tricky. Because I've taken an orange out of that bowl, there are 11 pieces of fruit left in the bowl now, and only 3 of those 11 pieces of fruit are oranges. So the probability of choosing an orange after having already chosen an orange is 3 out of 11. Okay, this number has gone down by 1 because I've chosen an orange. So now there are only 3 left, and there are only 11 pieces of fruit in the bowl. So it's a little different here. Now, for a mandarin, there are still 5 mandarins in the bowl because I took an orange out the first time. So that means there are still 5 out of 11. So this one here is 5 out of 11. You can see I'm running out of space here. And this one here is going to be 3 out of 11. 3, 3, and 5 adds up to 11. That's good. Now, if I had chosen a mandarin to begin with, there would still be 4 oranges in there. So that would be 4 out of 11. The mandarin, well, that's now 4 out of 11 as well because I've already taken 1 out. 4 out of 11. And the apple, well, there's still those 3 apples left in the fruit bowl. Who likes apples? Don't know. Not here. Well, here we go. We've chosen an apple the first time. Then, how many oranges are left in the bowl? There would be 4 oranges out of 11. Now, sometimes these go on and on and on, and sometimes these numbers are reducing, sometimes they're not. It depends on whether or not we are replacing those things we've taken out. But this is a nice example where I take something out and don't put it back. Okay, now we've got that one, 4 out of 11. How many mandarins? There's still 5. 5 of my 11 pieces of fruit are mandarins at this stage. Or, if I choose an apple, well, there's only 2 left now. There is a 2 in 11 chance of choosing an apple after having already chosen an apple. That'll do for our probability tree. We can find, now remember we can put our sample space down here. This would be orange, orange, orange mandarin, orange apple, etc., etc. And, right, listen carefully, this is the important part. Well, it's one of the important parts. This part here is important too. To determine the probability, just the same as we do with a probability tree or a tree diagram, of this outcome here, where I get orange, orange, I multiply those 2 things together. 4 twelfths times 3 11ths would be, here's magic, 1 over 11, because 3 fours are 12, and cancel 12. Okay, 1 over 11 is going to be the probability of 2 oranges, etc. Now, let's see what questions we have. Right, use a probability tree. We have drawn that. If you are asked to draw a probability tree, that is a probability tree. Sometimes in HSC questions, you are given some blanks in here that you need to fill in. Okay, rather than draw the whole tree, because it's quite a lot of work, sometimes you get part of the tree and you have to fill in some blanks. Probability of 2 oranges, we said. I'm going to say P, O, O. That looks like the origin, but no, oranges, not the origin. Orange, equals 4 over 12 multiplied by, right, multiplication principle, 3 over 11 equals 1 over 11. There is a 1/11 chance of choosing 2 oranges. 2 apples. Probability, apple, equals 3 over 12 multiplied by, here's my other apple, 2 over 11, I think that equals 1 over 22. Yeah, how do you like them apples? There you go. Pretty sure that's right. I think that's right. 6 to 2. Yep, 1 over 22. There you go. An apple and an orange. Now that could be, think about this, apple and an orange, or it could be orange and an apple, right? You're still going to end up with one of each. So that gives me, okay, because this hasn't, when it's and I multiply together, if it's or I add them together, as long as they don't overlap. Careful. Now, let's say apple orange first. That's, better make sure I'm in screen here. 3 over 12 times 4 over 11. Right, that's the apple followed by an orange, plus, right, because it's an or, orange followed by the apple. That's 4 over 12 plus 3 over 11. Did I say plus? It should be times. 4 over 12 times 3 over 11. I'm pretty sure that works out as 1 over 11 plus 1 over 11 equals 2 over 11. The probability of choosing an apple and an orange in whatever order is 2 over 11. Multiply the probabilities when it's and, add them when it's or. Now, probability that I do not get a mandarin. Well, does that mean I get an apple and an orange? No, it could mean I get 2 apples. Could mean I get 2 oranges. Right, so let's look at all of the outcomes that do not include a mandarin. Well, is there a good way of doing this? It is, I have orange first, so I've got 4 over 12, right? So start with an orange, another orange, 3 over 11, right? That's one of them. And I've got an orange multiplied by apple, 3 over 11, okay. Right, that's orange first. The first thing I get is an orange. There's no mandarin. Or I could start with an apple first. So what are my options here? Apple, orange. We know that's, what was it? 3 over 12 times 4, what was it? Over 11. Right, that's another one. And I want apple now. That's 3 over 12 times 2 over 11. Alright, what does that equal? This is 1 over 11. And here I have a 1 over 11. And here I have 1 over 11. And here I have, I think I get 1 over 22. Is that right? Yeah. So this would be 2 over 22. Another 2. 2, 4, 6, 7 over 22, I reckon. Okay, probability trees are a good way for solving more complex problems. You do need to draw them out. There are the same limitations we have for tree diagrams. Okay, but these are quite common questions, to be honest. These are quite common questions. Be careful as to whether these numbers are reducing as you go along. Right, but read through that, check it out, see if I have made a mistake, let me know. One more quick example and we will be done here. 2 tickets in raffle, 100 tickets are sold, there are 2 prizes. So we need to draw our diagram. I'm going to press pause here because it'll take a long time. Alright, I'm back. I feel out some stuff, the video's getting long. Here we see what's happening. There are 2 prizes, so first prize, second prize. I got 2 tickets, start off with 2 out of 100. And then let's say if I win, well, I've only got 1 ticket left in the draw, so it's 1 out of 99, right? We've got our fairly similar looking probability tree there, sometimes called a weighted probability tree. Right, have a close look at that, see if it makes sense. There are some questions here. Probability wins first prize. Well, we said, for the first prize, he's got 2 tickets out of 100 in there, so a 1 in 50 chance. First and second, and means I multiply those two things together. I get 1 over 4,950. Probability that gets no prizes, right, is not the complement of this. No, because there's something else in between where he gets maybe a prize, first or second. So, no prizes, 98 over 100 times 97 over 99 gives me this figure here. Now, this is what I really wanted to come back and talk about. We have a question, at least one prize. Where you see that word or that phrase, at least, we're normally talking about the complement. Now, think about this. What is the opposite, if you like, of winning at least one prize? Could we say that he either wins no prizes or at least one prize? One of those two things happens. Either Joe wins no prizes or Joe wins at least one prize. Right, one of those two things has to happen. So, we've already worked out how likely it is that he gets no prizes. It's this number here, 4753 over 4950. So, together, this plus my answer must add up to 1. So 1 minus this answer, right, the complement of no prizes is at least one prize. It's 197 over 4950. Check it out. If you've got any questions, ask me. But that's it for our video. Make sure you watch it. Maybe watch it again. Fill out your notes. Ask me some questions. See you in class.